Imagine looking up at the night sky and seeing only small, steady points of light. Stars, perhaps a faint band of the Milky Way, maybe a blurry patch that an astronomer calls a nebula. From such modest observations, how could anyone dare to say that the universe itself has a history, that space and time are stretching and changing? When I say the universe is expanding, I am not just telling a poetic story. I am making a very precise claim about the invisible fabric in which all stars and galaxies are embedded. There's a line by the poet Rilke that I like very much. He writes that we are the bees of the invisible, collecting the honey of the visible world to store it in a golden hive of the unseen. As a physicist, I feel close to that image. Light from distant galaxies, spectra, redshifts, tiny shifts in wavelength. These are the visible flowers from which we gather data. Geometry of space-time curvature expansion. These are the invisible structures we try to reconstruct. When a physicist today says that the universe has a history, what is actually being claimed, and how is it different from the creation stories that human cultures have told for thousands of years? At first glance, both seem to answer a similar question: how did everything begin and how did it come to be as it is now? For many people, the universe simply means all that exists. And the history of the universe sounds like a grand narrative in the same family as the cosmogonies studied by anthropologists. You and I inherit those images almost without noticing, a world emerging from chaos, from an egg, from water, from a God's gesture. They have deep symbolic and spiritual value, but they do not behave like scientific theories. Many creation stories are not meant to be tested, measured, or corrected. They belong to the realm of meaning and identity. Modern cosmology, in contrast, tries to treat the universe as a physical object that can, at least in part, be described by quantitative laws. From the 16th century onward, with Galileo and his successors, a new idea quietly took shape. There is one universe made of one kind of matter, obeying the same rules everywhere and everywhen. Stones on a hillside, planets around the sun, and stars in distant galaxies are all built from the same ingredients, governed by the same equation. How could a simple image of a falling person lead to the idea that space-time itself can curve Newton's view of gravity, the one many of us first learned imagines a force acting between masses, pulling them together across empty space. In that picture, the universe behaves like a fixed stage, and objects merely respond to an invisible attraction. Such an intuition is powerful, but it reinforces the idea that space is a passive background. If space is just a background, it cannot have a history of its own. Einstein began to challenge this view with a thought experiment he later called his happiest idea. Imagine you drop an object while you are in free fall. During that brief moment, you would see the object float beside you weightless. You would not feel your own weight either. In that situation, the usual sense of gravity seems to disappear. Einstein recognized that this was not a trick of perception, it was a clue. Free fall can locally mimic the complete absence of gravity. From that insight came the equivalence principle. Acceleration and gravity are two sides of the same physical phenomena. Years of work followed, supported by mathematicians who helped Einstein translate physical intuition into geometry. In 1915, he presented general relativity, a theory in which gravity is not a force, but the curvature of space-time itself. Instead of imagining two bodies pulling on each other, we imagine matter and energy shaping the geometry around them and objects following the straightest possible paths allowed by that geometry. You and I feel gravity not because something drags us downward, but because Earth has curved the space-time in which our bodies move. Einstein's field equations describe this relationship in two complementary pieces. One telling how matter and energy are arranged, the other telling how space-time bends in response. Matter instructs geometry how to curve. Geometry guides matter on how to move. Once gravity becomes geometry, the universe as a whole ceases to be simply the collection of its contents. It becomes the space-time fabric itself, with properties independent of the objects embedded in it. Many people still picture the universe as the simple sum of all things that exist: stars, galaxies, gas dust, and perhaps some dark matter in between. In that picture, if you remove a galaxy, it feels natural to say that a piece of the universe has been taken away, leaving a hole. General relativity invites a different view. When you remove the galaxy, matter disappears from that region, but space-time itself remains. The place does not vanish. The container is still there, even if some of its content is gone. Modern cosmology, therefore, treats the universe as a four-dimensional space-time, not as a mere catalog of objects. That space-time is elastic and responsive. Mass and energy bend it. Radiation and fields contribute to its overall shape. Einstein's equations allow us to calculate not only how a single planet moves around a star, but also how the global geometry of space-time behaves when averaged over enormous scales that include clusters of galaxies and the voids between them. Picture a flexible sheet rather than a rigid box. Objects resting on the sheet can deform it locally, creating dimples and curves. At the same time, the sheet as a whole can stretch, compress, or ripple. In the relativistic description, the universe corresponds to that sheet. Galaxies trace paths on it, but the sheet itself is a physical entity with its own possible patterns of change. You and I occupy one small region on this surface, yet our motion and the flow of time we experience are tied to its overall geometry. Once space-time is recognized as dynamic, a natural question follows. Do Einstein's equations permit a universe whose space-time remains eternally unchanged, or do they tend to produce universes that expand or contract? Confronting that question led Einstein to a difficult choice and to a term he introduced: in order to preserve the static cosmos he initially preferred. Physicists of the early 20th century largely assumed that the universe on the biggest scales must be static. Stars might live and die, galaxies might move modestly, but the overall cosmic structure was imagined as fixed. Einstein shared that intuition. When he applied general relativity to the entire universe, he discovered something unsettling. The simplest solutions to his equations were not static at all. They tended to expand or contract. Nothing in the mathematics naturally held the universe still. A dynamic universe carried implications that many researchers of the time hesitated to accept. If space-time could evolve, then perhaps it had a beginning or would have an end. That idea felt metaphysically charged and scientifically premature. Faced with equations that refused to describe a stable universe, Einstein made a deliberate modification. In 1917, he added a new term to his field equations, the cosmological constant. Explained in everyday language, the cosmological constant acts like a uniform outward pressure built into space-time. Gravity produced by matter and energy tends to draw everything together and curve space-time inward. The cosmological constant pushes back, supplying a gentle repulsion that can balance gravity on very large scales. With the right value, expansion and contraction cancel, producing a static solution. Einstein used this balance to construct a model of the universe that matched his intuition, quiet, eternal, and unchanging in its global form. Astronomers of Einstein's time looked at faint patches in the sky and called them nebulae, assuming they were clouds of gas inside the Milky Way. That assumption shaped how the universe was imagined, one galaxy only containing everything. Changing that picture required two kinds of measurements distances and the motion encoded in light. Edwin Hubble began with distances. Using the 100-inch Hooker telescope at Mount Wilson, he observed Cepheid variable stars inside several nebulae. Cepheids brighten and dim with a period tightly linked to their true luminosity, which lets astronomers determine how far away they are. When Hubble measured Cepheids in Andromeda, the result was unmistakable. Their distance placed Andromeda far beyond the boundaries of the Milky Way. Andromeda was not a cloud inside our galaxy, it was another galaxy altogether. This discovery expanded the scale of the universe by orders of magnitude. While Hubble worked on distances Vestos Slipher focused on motion using spectroscopy, by spreading the light of a nebula into its component wavelengths, he could examine the positions of spectral lines associated with elements like hydrogen and calcium. Slipher noticed that for most distant nebulae, these lines were shifted toward longer wavelengths. The shift indicated that the light had been stretched, a sign that the object was receding. In simple terms, the spectral fingerprints of the galaxies had slid toward the red. By combining Hubble's distances with Slipher's redshifts, a pattern emerged. Galaxies farther away exhibited stronger redshifts. Hubble interpreted this as galaxies fleeing from us through static space like embers from an explosion. Georges Lemaitre approached the same evidence from a different angle. He was trained in general relativity and understood that Einstein's equations do not treat space as an empty container. Space itself can evolve. When Lemaitre revisited Hubble's distance redshift data, he did not imagine galaxies flying apart through rigid space. A simple analogy helps imagine dots drawn on a balloon. As the balloon inflates, the dots do not crawl across its surface. They stay fixed, but the distance between them increases because the surface stretches. Lemaitre proposed that galaxies behave in the same way. Their redshift comes not from their own motion, but from the stretching of space carrying their light. When wavelengths travel through expanding space-time, they lengthen. This interpretation avoids the need for a cosmic center. Every observer anywhere in such a universe sees other galaxies recede with recession speeds increasing with distance. That pattern arises automatically if the metric expands uniformly. When you and I look at a galaxy spectrum, we are not reading its speed through space. We are measuring how much the universe has stretched during the photon's journey. Once expansion became accepted, the next question followed naturally: does the rate of expansion change? Over time, intuition suggests it should slow down. Gravity, even when weak on cosmic scales, still pulls matter together. If galaxies and clusters attract one another, then the overall expansion ought to decelerate gradually. Many cosmologists expected exactly that. You and I might have imagined the same a universe that expands rapidly at first, then coasts, perhaps even reverses its motion over immense time scales. Late in the 20th century, observations challenged this expectation. Two independent research teams studied type Ia supernovae stellar explosions with highly predictable intrinsic brightness. Because their luminosity is known, their apparent faintness tells us how far away they are. When distant supernovae were measured, they appeared dimmer than deceleration scenarios allowed. Their distances were greater than expected, implying that expansion had sped up rather than slowed down. In everyday terms, it resembled watching taillights on a highway recede faster than any simple model would predict. The evidence indicated not just expansion, but accelerating expansion. To explain such behavior, cosmologists introduced a component that acts like a large-scale repulsive influence, dark energy. It does not push in the way ordinary forces do. Instead, it arises from the properties of space-time itself. From the poetry of Rilke to the spectra of supernovae, modern cosmology shows a consistent pattern. The visible world offers clues that point toward an invisible but measurable history of space-time, a history still unfolding and far from fully understood. We began with a simple question: what does it mean to say that the universe has a history? Along the way, the question shifted. It no longer referred to a sequence of events occurring inside a cosmic container. It came to mean something deeper. Does space-time itself possess a dynamic, measurable past? Thank you for spending this time exploring the history of space-time. Each time you look at the night sky, you are seeing not just stars, but a cross-section of the universe's past. In the decades ahead, new observations will offer new surprises.